Hi, everybody, and thank you all for choosing to be here today instead of going to the beach. The subtitle of my presentation could be easily how to do SSA on a limited budget. And since this work was really part of our close collaboration with the United Kingdom, I would like to use this occasion to thank my UK colleagues for helping us to move into this area. They're here in this room today. So, or shall I put it, showing us the right path. We are hoping that we will continue this collaboration. So it all started with our joint plans to observe the shallow re-entry of ATV-5. Now, as you know, that never happened, but we ended up observing some other satellites using a combination of scientific CCD cameras and standard DSLR cameras, wide field lenses 20 to 60 degrees in the sky. We observed a total of 60 satellite passes of 44 different objects from 2 locations. And we basically recorded satellite traces against the stellar background, mainly observing the LEO objects. And the total number of images that we took was over 2,000. As a result of this project, we developed software for automated astrometric analysis, and that's what I'm going to talk to you about today. So these are all should be considered as our initial steps in building the SSA capability at the Defence Technology Agency in New Zealand. So here you see our 2 beautiful locations. Although I'm not working for the New Zealand tourism industry, I can strongly recommend that you, if you have a chance, visit some of these locations. It's not so often that you can do your science from Middle Earth, or, as we did, observe satellites from Rohan. So you can see Mount John Observatory and also NIWA station. NIWA stands for the National Institute of Water and Atmospheric Research. Now, the equipment was pretty standard, low-cost set of cameras, CCD cameras with standard off-the-shelf lenses, and simple equatorial mount for sidereal tracking. Here you can see an example of image that we took during this trial. You can see, for those of you who have never seen the southern sky, you can see the Large Magellanic Cloud, and you can see a satellite leaving its trace just north of the Large Magellanic Cloud, moving slowly through the constellation of Dorado. The total exposure time was 6 seconds. However, the actual effective photon collection time was a bit shorter because we introduced some gaps in the satellite trace by manipulating the mechanical shutter in order to introduce some more reference points. The main result of this work was the development of an automatic algorithm for the reduction of our images and basically for the astrometric calibration. The software is called StarView and is capable of fully automated blind identification of the stellar field and selection of a large number of reference stars. The software was written in Delphi. and typically uses about 1,000 stars or more. Gaussian profiles are fitted in both directions to every detected star. And then we use a special algorithm, which I will explain in my next slide, of automatic identification of the stellar field, which we call stellar fingerprints, which is extremely fast and reliable. And once the identification is finished, the software then computes the astrometric solution as a set of two-dimensional polynomials to the data. Typical RMS error is about 1/10 of a pixel, which turns out to be between 6 and 10, more frequently about 7 to 8 seconds of arc. And that corresponds to about 15 to 25 meters at a typical LEO range. So what are stellar fingerprints? A fingerprint of a star is simply a small circle in the sky where every other star in the neighborhood has a set of polar coordinates to define its relative position to the central star. We generate two images for each of these fingerprints, one-dimensional images representing the distribution of the position angle and the distance from the center, which we called theta comb and rho comb. The rho comb is on a logarithmic scale so that we can cross-correlate two similar fingerprints in order to determine the scaling factor. And when we cross-correlate to theta combs, we determine the image rotation. And just a quick demonstration of how it works. Here is a beautiful CCD image of a region in the southern sky with the Large Magellanic Cloud there again. So the first step is detection of stars in the image, which is standard thresholding algorithm. And here you see some stars detected. Red means detected but not yet identified. And here is when our fingerprint algorithm starts. The software chooses a bright star in the image, creates a fingerprint from that star, and then looks into the database of 20-odd thousand fingerprints from the catalog. We use simply Hipparcos catalog because all these stars are relatively bright anyway. And here is the identified fingerprint for the central part of the image. Blue means identified. The next step is, I'm not sure if you saw what happened here, but some of the red squares turned into red diamonds, which means some of the stars were selected as core stars. Core stars we define simply as a subset of all detected stars, but more or less evenly distributed across the image. And then another algorithm kicks in, using the initial identified region and building up the astrometric solution one star at a time. We recognize all the core stars in the image, and they are identified as at the end of this part of the algorithm. And in the last step, in one step, all the other stars are identified. And as I said, typically 1,000 stars are ready for the astrometric solution, which is a simple linear least squares fit between the pixel coordinates and the equatorial coordinates. We have also here, we can see the plot of the residuals for closer inspection, just to make sure that there are no systematic deviations. And just as an illustration for this astrometric solution work, I have picked a set of satellites that we observed on one particular night. And I wanted to compare our measured positions with the predicted positions using the TLE orbital elements. Now, you should notice, if you look at this table, that looking at the last column, that some of the orbital elements are really outdated for some of the satellites, but these are the best orbital elements that I could find on the Space Trek archive. So I compared the measured positions from our satellite trail, which is marked as alpha and delta on this image, and I measured the distance between that point and the predicted point on the predicted trajectory. And just to make it simpler and easier to analyze, the error is actually divided into two components, lateral and longitudinal. Lateral is perpendicular to the predicted trajectory, and longitudinal is along the trajectory. Here is a plot of prediction errors for this bunch of satellites on a logarithmic scale so that all could fit in nicely. You can see that there are some satellites there that are that show really low prediction errors, under 100 arc seconds, while there are some others, especially in the upper right corner, that show huge errors, and those are actually the satellites with rather poor orbital elements. The same distribution now in kilometers at the satellite range, showing more or less the same, but you can see that those well-behaved satellites are mainly within 100, 200 meters up to a kilometer, while the others are of the order of even tens or 100 to 200 kilometers for those cases with poor orbital elements. That's basically it. I don't have a summary slide because I thought my presentation was more or less a summary of our work. But in one sentence, what we demonstrated is, I believe, that it's possible to use inexpensive equipment to accurately measure positions of satellites that can be used, say, in any attempt to improve the orbital models, or at least improve the orbital parameters. Thank you very much.
We do have time for one quick question.
Just, well, this isn't really a question, it's just mainly a comment. In using TLEs, you know, they're not that accurate. So I just wanted to let you know, there are sets of satellites that you can get very accurate ephemerides that you can use for calibration purposes. And the other comment on TLEs, I think you were looking at mostly debris, but if it's an active satellite, sometimes there's a lag between when they get posted and if it maneuvers, so you can potentially get some inherent error.
Yes, thank you. I totally agree. We are aware of that, and my plan is to use some better predictions to properly test this. So the whole point here wasn't really to do that part of the work, mainly to illustrate what can be done.
Okay, thank you very much.
Okay.
For a little excitement, we have a slightly different speaker coming on for the next talk. Mark Retton is going to speak for us. He's from Australia, and he's talking about intelligent sensor control for autonomous catalog building and maintenance.
Thanks. So my name is Mark Retton. In the agenda, it's Travis Bessel, but most of this work was done by Tyler Hobson at UQ. I'm just here to sort of take the credit. So what I'm going to talk about is Tyler's developed this technique he's called SPARSE, which is designed for incorporating uncertainties into orbit propagation and then It's an intelligent way of steering your sensor in the right place to go searching. So if your uncertainty is much bigger than your sensor field of view, then you're not going to be able to slurp out everything at once. So you might need to look a few times to cover that region of uncertainty. And so Tyler's built an intelligent technique for doing that. So what we've done is extend his technique, which was designed to take a really old orbital information, a TLE, and propagate it forward for weeks or months, and then go looking for it again. So what we've done is modify that and say, instead of an old orbital information, let's try and do initial orbit determination. So given a sequence of angles measurements, let's initiate his spray the particle filters out, the particles from his particle filter out over a region of uncertainty and propagate that instead. So I'm going to show you some trials that we did to demonstrate this technique. So brief review. So on the left, your left, the blue boxes are essentially a standard filtering recursion prediction, so time update followed by observation, take some measurements, and then you do a measurement update. So you incorporate the measurement information into your filter and refine your estimation. So what sparse gives you is 2 extra steps. So you do your prediction, and then based on where you think is the best place to look for your target, you steer your sensor, you make an observation, and then what you can do is you either saw it or you didn't see it in that particular direction. And the fact that you didn't see it also gives you information. And then based on that, you can either do a measurement update or then go to do your prediction again. And because we have significant nonlinear dynamics, we have a nonlinear measurement function, the particle filter is the right solution. On the right-hand side, we're using a technique known as the constrained admissible region to do initial orbit determination. So basically, that means that rather than saying, so we take a sequence of measurements, we take angles and we infer angle rates. So that gives us 4 dimensions of the 6 that we might want to measure. So what we're going to do is we're going to say, we're going to assume that our class of object that we're going to measure is a certain type of, has a certain type of orbit. And in this case, we're going to assume it's a geo. So we're going to constrain the semi-major axis and the eccentricity of the objects to match what most geos look like and do our initial orbit determination that way. Skip that one. So what we're going to do is combine initial orbit determination and sparse, the smart steering, and encapsulating the uncertainties. So we're going to start off with a geoscan, which is essentially a catalogue maintenance function, right? So we've got a 10 by 10 degree section of the sky that we're going to scan through. In each direction, we're going to take 5 images. And those 5 images allow us to build up angles and angles rates of the objects in geo in that area. So in the first, so we're going to do a geoscan one night, and then several nights later, we're going to go looking for an object. So one of those objects from that geo, we're basically going to assume that we know about every object in that geoscan region, except for one. So one of those objects we know nothing about. So in the first trial, we're going to do this constrained admissible region particle filter for initial orbit determination, and we're going to go looking for this object. But in the first trial, we're going to sort of assume that the data association problem is solved for us, so we know whether actually know whether we've seen the object or not. In the second trial, we automate it. So we actually have a catalogue of 50 or so objects that are in that geoscan region, and we propagate that entire catalogue. Just so happens that one of the objects we've marked, one of the objects as not being found, so we do initial orbit determination on that in the first geoscan and propagate that forward. It'll become obvious in a minute. Right, so this is our equipment. small telescope, smart mount, some smart software, the particle filter, all happens in real, the astrometry, image processing, all happens in real time. So this is an example of what Tyler calls negative information, right? So we've propagated forward 2 days. So we've done our initial orbit determination using the constrained admissible region. We've propagated forward 2 days. We've looked in a direction where we think it's most likely that object's going to be, and it's not there. So the red particles, and just notice they're nice, sort of smoothly distributed. The telescope's looked in that direction, hasn't seen what it was looking for, and so it's notched out that area of the PDF. So next time we go to look, it knows not to look there. So basically that happens twice. So we look sort of here, then we look here. Oh, it's a bit jiggly, isn't it? We look here, and then we look over here. So on the third go, we find it. And so all the red particles, which are positions where the object might be, collapse down to a single point, well, effectively a single point, because we actually saw it. So the filter does its update process, incorporating the information from that measurement. All right, so the second trial, so the first trial we did manual data association basically. So we told the filter whether or not that measurement actually came from that object. In the second experiment, we said we're actually going to do it all automatically. We're going to do automatic data association. We're going to carry around a full catalogue that covers that region except for one object. So what we're going to do, so there's a second thing as well, right? So this is essentially our constrained admissible region. This is eccentricity along here and semi-major axis along here. And in the first case, what we did when we did our initial orbit determination was we got our particle filter to spray particles uniformly all over this region. And so basically saying that, you know, this is a geotype object, it's going to have this bounds and semi-major axis, this bounds and eccentricity. But what we've done here is we've plotted every object in the catalogue that fits within those bounds. And it's pretty immediately obvious that the vast majority of things sort of stick along this distinct line, right? It's intuitively obvious that's going to happen. So why are we spraying particles out in this region and this region and this region and this region when we know it's really unlikely that there's going to be something there? So the way we've done the initial orbit determination in this case is basically we're going to preferentially treat the objects that we know are likely to be geo, right? So we're going to say if it's a geo object that we see, and we are assuming that because that's what our admissible region says, we're going to preferentially treat it along all of the existing objects and essentially de-weight the rest of this region. So it's hopefully going to give us a faster way to reacquire the object because we're using more information, we're encoding more information about what a geo object actually should look like. Right, so this is the example of the second trial. So the first trial, the distribution was red, now it's green for no real reason. But you'll notice the striations in the pattern here. And that's because of that clustering the particles around those strong semi-major axis sort of locations has meant that you get this sort of more distinct pattern instead of sort of being uniformly smeared out. And in this case, so this is after a few nights, we've done the geoscan, predicted forward, automatic data association. The density of the particles has said steer in this direction, and we found it on the first go. The second field trial was exactly the same. So predict forward for a few nights, look in the direction of the highest density of particles, and we found it on the first go. Unfortunately, I would have liked to give you an example of a more difficult object, an object that's not necessarily clustered around that sort of higher density region in geo. But yeah, time was an issue. I guess this is a slightly more interesting one with an object with a slight inclination. So you can see that the particles have tried to capture that inclination through the predicted distribution. Okay, so basically the two key points, right? So we've got an algorithm that can accurately represent the uncertainty in an orbit, predict it forward for several days, and then go off and find this object by intelligently searching through the uncertainty in or the distribution of the orbit. So we've combined that with an initial orbit determination technique, which allows us to not only track things that we knew about that were old, but track new things as well. We've done it automatically, so we have automatic data association. We have only tried it on one object, but it should be extensible to more. And the last thing is that our initial orbit determination technique includes more information about what a geo object should look like. So rather than assume uniform bounds in semi-major axis and eccentricity, we can encode more of that information about what a geo should look like. And I think I've covered that. Thank you.
Yes, questions?
Yeah, hi. So how does your algorithm choose where to look first within the region? And then if it doesn't find something there, how does it continue to kind of search through these particles?
Yeah, okay. So it's the data association problem I was talking about. So essentially, you've got a distribution of particles. It looks for the densest region within your sensor field of view and looks there. And then the second bit about whether it knows whether or not it's seen it is it's the data association problem. So effectively, if you look in a region and there's multiple objects there, if they're already in the catalogue, they're going to have tight clusters of particles around them already, and those measurements are going to get very low weights for the distributions that's really spread out, right? So the known objects get preference for those measurements effectively. So it happens automatically.
Thank you.
Yeah. So, I mean, there's obvious complications where you observe an object you haven't seen before and there's more than one object in the field of view.
Okay, you've got about 38 seconds. Go.
Well, you're starting to hint at it there, but yeah, what about the cross-linking problem? Because you've got a lot of objects up there, and they vary in flux. And so, I mean, you start off looking in the most dense region, but how do you know that you've actually found the second occurrence of that object, and it's just not some chance occurrence of another unknown?
Yes, that's exactly the data association problem. And the way that we've constructed this trial was that we've assumed that we know everything else, and there's only one that we don't know about. But yeah, certainly there would be, you would need to manage the uncertainty if you knew if you were actually doing catalogue maintenance and there was more than one object you didn't know about. Yeah.
Okay, thank you very much.
Thanks.
Thank you, everyone. My name is Sam Wooten. I am from the MITRE Corporation. I'm here on behalf of the GEODS Program Office, SMC SYGO. Pardon my congestion. I hope it does not become a problem during this briefing. Also, I just finished a giant espresso, so hopefully you can all keep up. So I'm switching gears. We've heard a lot about capabilities and algorithms, and I'm not going to be focusing on that, especially within GEODS. Rather, I'm going to be focusing on the modernization of the data processing subsystem in which these capabilities and algorithms can integrate. So a little brief history on GEODS in case you all don't know. GEODS is the ground-based electro-optical deep space surveillance system. It's been operational since the mid-1980s. It operates in a 3-location, 3-tower configuration, as noted there on the right. Those are the 3 sites: Socorro, New Mexico, Diego Garcia, and here in Maui. GEODS is the key contributor of deep space observations as part of the Space Surveillance Network. And its most recent significant modernization was in the 1990s. This is important because we all know that hardware and software technology has profoundly evolved since then. So just to jog your memory, I threw up a couple images there just to remember what life was like back in the early 1990s. I know the most important question you're all asking right now is that me? No, that is not my yearbook photo. But lucky for my wife out there in the audience, there is a strong resemblance, just not in the wallet. I do want to point your attention, though, towards that computer in the middle. That's similar to my first computer that I received about 1991, 1992, an IBM 386. Had a whopping 25 megahertz processor, 1 meg of memory, and 129 meg of storage. We did upgrade that computer to 2 meg of memory for about $200. Now, I want you all to imagine keeping that system alive and as your only PC in your house, even to this day. And this is some of the challenges GEODS is facing, especially from a data processing perspective. So the current System Program Office, or the SPO, as I mentioned, SYGO, they're executing a rapid and aggressive vision. And this vision is committed to providing premier space surveillance via ground-based optical mission systems. The sustainment contractor, Harris, has been working closely with us to execute this vision. We also have been exploring partnerships and integration opportunities with many SSA capability providers, and many of those are listed there on the right. This does not, by any means, preclude any of the additional partners that may be here in the room. We are exploring this vision, and we need help. As it's been mentioned throughout the week, looking at the commercial world, academia, and industry to provide these capabilities, we know that's important, and we are actively pursuing partnerships with you all. There on the left is a marble chart I actually created, which categorizes all the major releases coming up, either in the past and in the future. And these are the execution years. Granted, it may take a while to actually build the capabilities and release them, but I just want you to point out how I categorize these capabilities together, be it mission hardware, mission software, communications, or computing infrastructure. It's important to note that if you look at the green marbles, those are the software releases, and there's significant software releases coming out every year. And this just means that we need a more robust, better computing infrastructure in which to integrate. So now I'm going to get into these modernization efforts. The first is Service Life Extension Program, or SLEP. The primary goals of SLEP are to extend the technological life of the system through a multi-phase approach. And currently, we are executing phase 2 right now, which is focused on the data processing subsystem. Another goal is to ease long-term sustainment costs, and that can be attained through using COTS-based when appropriate. There are also secondary goals specific to phase 2, the ongoing effort right now, to lower the cost and therefore the complexity of new SSA capability integration. We also are looking to ease the computing hardware expansion in which to integrate these capabilities. So another way to look at SLEP is it's the computing hardware. That's what's being modernized first. In close alignment with SLEP is the data processing software modernization. This is focused specifically on software architecture. GEODS, since it has been around since the 1980s, it's been through 30 years of past sustainment across multitude of companies, developers, and leadership. It's been very difficult to sustain and thus integrate capabilities and algorithms into the current architecture. You could think of it as a ball of yarn or a plate of spaghetti. A lot of developers, myself included, are very familiar with spaghetti code. It makes it very, very difficult to let alone maintain, but also to then integrate new capabilities into. And currently, right now, prototype services are being prepared for operation. So just to dive a little bit more into these hardware and software modernization efforts, some features of the hardware modernization include virtualized hardware, which will drastically improve system maintenance and also performance. We are leveraging COTS-based x86 architecture, which will expedite procurement, sparing, and expansion. This also provides a scalable solution, both horizontally and vertically, which will simplify processing and storage expansion, which is critical for new SSA capability integration. From a software modernization, the goals are to look at the software messaging. The current messaging software is archaic and unsupportable, so we are looking to replace that with a modern messaging solution. Additional goals include a loosely coupled modular architecture, and also make it a sustainable, flexible, and integrable architecture. Integrable is not a word I created. It's actually from the Software Engineering Institute at Carnegie Mellon University. Basically, what it means is that the interfaces are well-defined and well-documented. Why is this important? Because as you all look to develop new algorithms and capabilities, it'd be nice to know how to pull in the data that you need in order to drive these capabilities and algorithms. And having an integrable architecture is very, very important for this. As well as we are exploring now a microservice-based software architecture. Achieving all these goals makes everybody happy. That's why there's smiley faces there. So looking at now the software enablers. So why is a new software architecture needed? Because integration into the existing architecture is not expedient nor sustainable. There are plenty of Harris people in the room who you can talk to, and you'll find out why. I will also discuss this in a bit. Again, the new architecture must be flexible, modular, and integrable. Additionally, the legacy code base and structure is not aligned with current and future software generations. This is extremely important to keeping GEODS relevant, because as the current development base is aging, how are you going to get the new talent? You don't want them to work, these developers don't want to work on something that's archaic and clunky to work with. They want to work on something fun. So that's what we're trying to do. And microservices represent an ideal solution to achieve these technical goals. Important to the SPO is also to look at how can we incrementally deploy a new software architecture versus the typical big bang. It can take years and years and millions of dollars in order to implement a new architecture, but doing it a big bang, there's a lot of risk. By incrementally deploying, that lowers the risk and helps to untangle that ball of yarn. And that image is just an example of a microservice architecture, which I will explain here shortly. So, microservices, what are they? They represent a paradigm shift in both architecture and development. Microservices, when coupled with proper software monitoring tools, can provide service monitoring, registry, and fault tolerance. I'll explain that a little bit more in a few minutes. There's opportunities for continuous integration, testing, and deployment, as well as it supports a DevOps paradigm. DevOps is gaining a lot of traction in the commercial world, and that's short for development operations. It's a collaboration of operations and development engineers throughout the entire development lifecycle, from design through development and then into production. Some of the features that can be had with the DevOps paradigm, you focus on end item delivery, the product quality, and you can improve that product quality through continuous insight into that final product delivery, as well as it supports continuous and automated testing, which will provide much better and robust code and less faults. A final feature of DevOps is reduced time to field. This is important for fielding SSA capabilities. How can we rapidly integrate the capabilities that you all are producing? By having this microservice environment coupled with the DevOps paradigm, we can hopefully and strategically shrink that gap. And the image below, I think, captures how software development is evolving. In no means does this represent a religious or scientific belief in evolution. The SPO wanted me to say that. But I thought it captured how software development is evolving into this continuous world. So this is a great image from Martin Fowler and Jim Lewis. I have to give credit to them. If you are interested in microservices, I highly recommend you Google Martin Fowler. He has some great articles out there. Basically, the monolithic is a traditional web service architecture, and this depicts the difference between the traditional and the micro world, or the monolithic. The monolithic features service functionality within an application or web container. Basically, all the services are built into one application. If one piece should fail, it brings down the entire application, and therefore, that results in downtime because you have to restart the application. It also features a large data management, a single database, if you will. That can provide problems during the data management and the sustainment. Within a microservice environment, each service has its own data management, so therefore it's very simplistic and therefore easier to sustain. Also, these microservices reside in their own container, and with the proper management tools, if a single microservice should fail, it will not bring down the entire application. Just that, and the monitoring tools can also restart those microservices, so therefore there's little to zero downtime. This is actually very, Amazon Web Services, Netflix, eBay, all these large capabilities actually implement this architecture today. So here's a brief example of how capabilities can be integrated. Today, the way the capabilities can be integrated, now imagine, remember the IBM 386 example I gave you, that is your only PC running in your house. What if you wanted to install Office onto that? The resources are not there within that 386. You would have to potentially go out and buy a new laptop, install Office on that, and then you have to play tricks and wire that into your home PC. That's not a very sustainable architecture going forward. Within a microservice architecture, as well as the hardware benefits gained from SLEP, that's what the bottom picture illustrates. So when the capabilities are being provided, they know how to interface with the data, and therefore they can plug in, literally, and subscribe to the data that they need, and then that software is then hosted as a microservice within their architecture, instead of running on a laptop or some other game. This is a very sustainable capability going forward. So in summary, based upon Geod's age and lack of recent modernization, it's primed for a hardware and software overhaul. The current SPO has an aggressive SSA vision currently under execution, and a more robust, scalable, extensible, and integrable architecture provides the needs to accomplish the SPO's SSA vision and therefore integrate with you all. And these modernizations efforts put in motion will allow Geods to remain sustainable, affordable, and relevant far beyond 2027. Thank you.
So I don't think I'm going to complain about my very clunky, heavy, lightweight government issue laptop again. Wow. We do have time for a couple of questions. Lucky.
A question regarding certification and accreditation for the microservices approach. Does the accreditation process, does it have an appetite for taking changes the way that this would work?
The SPO is complying with the cybersecurity processes that are put in place, and cybersecurity is baked into all processes going forward. It's not just frosted on at the end like traditionally it's been done. So we are actively exploring those and ensuring that we comply with all of those cybersecurity practices and procedures.
Okay, thank you very much. The very last talk of the session is by Phil Bland from Australia. He'll be talking about adapting a planetary science observational facility for space situational awareness.
My name's Phil Bland. I'm a planetary scientist. I'm going to tell you today about a facility that we've built, a project that we've done in Australia, and essentially my goal here is to find out if any of the things we can do have relevance to this community. So the project that we've done, the principle is essentially we want to track fireballs coming through the atmosphere and work out where mostly meteorites land and where they come from in the solar system. And the logic behind that is that meteorites are kind of a great resource for understanding the early solar system, but we've got no constraint, we've got no context. So as a geologist, you always want to know which outcrop your rock came from, and that's really what the camera network can give us. This is the network as it currently stands. We've got 50 stations across Australia, covering around about a third of the continent. Each one has, we've got obviously all the logistics for that, comms, power, storage, so that they're completely autonomous. This is an example of one of our stations at Mount Isa in South Australia. So you can kind of see what that roughly looks like. Early on, we made a decision to go with off-the-shelf DSLRs rather than astronomy-grade cooled cameras. The logic there is simply that we had, a power requirement. We wanted to be able to power them with a small number of solar panels, so that's why we went with that. And on this, you can see we've got a fisheye lens, and next to it, a smaller fisheye video. So our cameras, they're built to operate for a year in the middle of Australia. They can store all the imagery collected over that period. So one camera gets about 1,000 images a night, 30-second exposures. And the whole principle behind it is that they're cost-effective and easy to upgrade. So, in this, we let Canon and Nikon do the hard work and bring out the next generation of camera, and then we can just plug that in. Neural network algorithms spot the fireballs, and they report those to us, so we can get essentially a kind of a real-time update on whatever's coming through the atmosphere. So as I say, we use commercial DSLRs. At the back of the lens, we've got a LC shutter. Flickering that off and on gives us velocity of the fireball as it comes through. But we realized that we can actually do a little bit better than that. If we modulate that shutter in a De Bruijn sequence, and I always get this wrong, but I think that means the longest non-repeating sequence from the smallest number of characters. So essentially, if we see within that 30-second exposure a fireball is recorded, say, half a second of it, we can get absolute timing for each dash in that half second. So it's in one image, in a long exposure, we can actually embed absolute timing to kind of sub-millisecond procedure, which makes reducing the data set, automating the pipeline a lot easier. We've not got to kind of look to another sensor to get timing from that. So a lot of effort went into the design of the cameras. Equally as much went into the trying to automate the entire pipeline. We kind of finally got to the end of that at the end of last year, having deployed the network. But right now, it's not completely tweaked, but we can get from an image, we can get a full position for a rock and an orbit in about 10 or 15 minutes. This is an example of one of our fireballs. We can see you get detail on fragments, so we can track individual fragments. And this obviously applies equally to space debris as it does to natural meteorites. And this is a triangulation of a fireball coming through the atmosphere. So this was over Lake Eyre South in South Australia. And that's kind of what that looks like as it's coming down towards the lake. So with this approach, so we use particle filters to do this with colleagues at DST Group. We can pinpoint the position of the object when it's luminous to within 20, 30 meters. The full position, the light goes out maybe at about 30 kilometers. And then when that happens, we have to do a whole bunch of wind modeling, climate modeling to work out how the rock is blown off course. So you get a bigger error on the ground. This is our current data set of orbits. For the blue are everything. The red ones are where we've calculated a meteorite should be on the ground. To give you a feel, so automating that pipeline, in this field, it was the first time that people had actually done that. So before then, there was about 800 fireball orbits for bright fireballs. That's really not great if you want to understand what's happening at 1 AU in terms of size frequency distribution of asteroid fragments and comet fragments, which you do because they're the things that hit us. Doing it this way, we've already got about 400 orbits. So we're getting a much bigger data set and unbiased as well. So as I say, we get the meteorites, we get fireballs that burn up in the atmosphere. We also get re-entering debris. with that sort of precision on the trajectory, we observed, so this is with the current network, Chinese burn from to geostationary, which was kind of interesting. And we've also seen astronomical events. So we saw a nova, and that kind of linked into where we were thinking of going it from there to target supernovae and other energetic astronomical events, which I'll talk about in a moment. So the logic here is that what I'm asking is, can we leverage some of the assets of the Desert Fireball network to give value from a space situational awareness point of view, if some of those other things aren't valuable enough already. So we've got logistics for all of those sites across Australia. So that's a long baseline, which I guess gives you a longer terminator window. Hardware, we know how to build very tough hardware, cost-effective hardware. We've got the data pipeline sorted. And for curious reasons having to do with Western Australia's desire to do mineral exploration as well as radio astronomy, it's actually very easy to get supercomputer time if you're a geoscientist. So there's a lot there that potentially we could apply to space situational awareness. So we considered, okay, an upgrade to the units that we could do for, say, transient astronomy. And this was in collaboration with some of my colleagues at the SKA. Our first idea here was just to go with a similar approach to what we'd used before, using the DSLRs, but get narrow angle lenses and then kind of lace those together so we could tile the sky and triangulate within tiles to, from their point of view, weed out satellites from the transient data set. But obviously, from your point of view, that is potentially a useful data set. So you would have a wide field, long baseline optical system. As I say, you basically tile the sky with about 28 systems down to around about 20 degrees. Our tests, we can get to a limited magnitude of about 13 in a 10-second exposure. And that means you've got a DSLR that's really survivable for a year, just churning through that 10-second exposures through the night and able to store all of that on hard disk. So you basically get a gigapixel image of the sky every 10 seconds to 13th magnitude. So this is an example of kind of one of our fireball images. And really the difference between what we get in one of our regular fireball images and what we can do with this like little upgrade. So these ones we use a 50mm lens and an equatorial mount. And we can zoom in. And you get kind of nice resolution. And we, needless to say, you point it pretty much anywhere, and we get lots of satellites. And we also see geostationary. So this is an example of kind of we basically designed that to have an easy upgrade for to get at astronomical events cheaply. But we can use the infrastructure of the network for anything else. So I'm just interested to find out, okay, can we use 50 stations across Australia that have power and comms and obviously permissions for all those sites, at dark sky sites, for other things. And is it useful to be able to track space debris and Chinese rockets? So that's me. Thank you very much.
Do we have any questions? Yes, Arthur.
Do you have to worry about vandalism, human or otherwise?
It's most of these places, so a lot of our cameras are on cattle stations, And some of those places you're about 100 kilometers away from the nearest other human being. So we've actually never encountered a problem with that.
So Charlie Bellows, you talked a lot about the storage capabilities of the system, but timeliness is an important aspect of SSA. Can you talk about how quickly you can get and process the data?
We've really not got into that yet. I mean, I've been talking with my colleagues on the SKA, and based on their experience with other transient surveys and software for that, I think one of them was involved in Pie of the Sky, which was a Eastern Europe one. We can get it with we should be able to get it with a kind of a reasonable upgrade to the hardware that we're currently using. So but that's all I know. Sorry.
Okay, thanks.
Could you comment on say the pixel accuracy you're getting at GEO? 10 arc seconds, 30 arc seconds, that kind of.
I can't. I'm sorry. Yeah, that was really kind of first test. It's basically, does any of this look useful? Yeah.
Yes.
Oh, okay, good. Okay, thank you.
How do you deal with nights where you have high moon illumination?
I'm sorry?
High moon illumination. How do you deal with nights?
Oh, full moon, did you say? It essentially means from a fireball point of view, you can actually, even if it's a dark sky site, they're so bright, you still get reasonable data on them. You don't get as many faint ones, but for the bright ones, it's not a problem.